Eastern Routes capital programmes. So here to talk to you about Browney Curve embankment stabilisation works. As you can see from the photo on the presentation, we've got a image from before we started on the site there, and a key quote from the Chief Civil Engineer for LNER in July 1895, highlighting the movement that was seen at the embankment at Browney back when the railway was built, or not long after the railway was built in this location. Browney Curve itself, it's on the East Coast Main Line, just south of Durham, about 3 miles south. If you pass it on the train, you are probably there in about 2 or 3 minutes once you've left Durham. The railway goes around the curve. You pass the River Browney, as you can see on the screen, to the right-hand side of the red box. And the worksite itself is highlighted in that red box. You just next to Cropsdale Viaduct, Gill Tunnel. Some of you may know it as well as Browney Curve. I'm not going to talk straight off the slide, so skip to that. The River Browney is obviously the key in this. The embankment itself is and has been slowly sliding towards the river over probably the past 150-ish years. 50 years, yeah. Obviously not at a great speed, but you're talking millimetres per year, which will ultimately affect the earthworks, affect line-side assets, the tracks, and as many of you have probably experienced in your careers, require regular maintenance there. Most of you probably worked in the vicinity anyway, and to undertake maintenance on Browney Curve or around Browney Curve itself. Got two, well, we name them as two landsides, but we've got the site itself is about 500 metres long, close to the road, close to the river. There's overall 40-metre drop between the road to the river level there. I'm going to pass you over to Andy for sure.
I think I'm there. Then you carry on.
Thank you. I think that's you.
Okay.
Again, it's the technical part.
Hello, everyone. I'm Gill. I'm head up the geotechnical team discipline for Pell Bushman across the UK, and I've been involved in the Browney Curve site for approaching probably 10, 11 years, something like that. So quite intimately involved in understanding the complex landslide complex. So if I press the top, is that the light? Put the switch on the side of the top. I'll point. Anyway, so typically the site is steeper at the top. So we've got the railway embankment with the steeper sides. The embankment side slopes around 1 in 1.8, 1 in 1.4, up to about 12 metres high at maximum height. The upper part of the slope above, between the road and the East Coast Main Line, tends to be steeper, and it flattens out, and much shallower slope below the railway embankment down towards the River Browney at the base. And this is a picture from 2018. Where you can see a steeper slope on the upper hillside, East Coast Main Line through the centre of the site, tree-covered embankment side slope on the riverside, on the upside, and sheep in the lower slope, and a much shallower slope down to the river. And this is from January last year, when some piling platforms started to go in, and the embankment side slope was cleared of vegetation. Early site timeline. So I think Tom's sort of gone through this, but the London to Edinburgh railway line through the site was constructed in 1872, and it was unstable during its construction. there were problems which I'll come to related to the ground conditions. The point where the embankment was constructed couldn't really have been any worse across the hillside. So they put borings down when they were found in the embankment and found a lot of wet sand. They had problems with excavations, finding a stable base, and subsequent investigations found a lot of stone and timber in the base of the below the base of the embankment. And I don't read that. A letter from William Armstrong and Bell's brothers, writing on behalf of Browney Colliery to Charles Harrison, the North Eastern Railway, dated 16th of June 1895. Basically says that your main line traverses this district of Lord Boyd's property and passes over some difficult shifting surface, which intermittently is on the move towards Browney. River Browney in this condition has existed before the construction of your line. So I think I'll carry on. So we cover this a bit later, but it was known that the site was unstable before they constructed the railway. And the reason why the railway was put through here was because of a wealthy and influential landowner didn't want it across their land. Timeline of the site. So it was constructed in 1872. There's a railway siding that was constructed in 1910. The colliery just to the north of the site. Browney Lane was realigned, so it's straightened up to its current course. Colliery closed, so they were related to flooded workings there, which aren't really connected to the instability of the site. The site had wooded areas. The river has changed its alignment on several occasions, and it was infilled on the meander was infilled to push the river further away from the toe of the slope to try to stabilise things. And things really started picking up in the 60s and 70s. So there was a slope failure on the upper hillside, and the first sort of significant amount of ground investigation information was undertaken in the late 60s and carried on into the 70s. And maintenance was undertaken throughout this time, and there were further changes with wooded areas being cleared, deep filter drain. So there's a significant deep drainage system that was put in the upper hillside above the between the road and the railway embankment, which seemed to improve things for some time, but they had problems constructing those deep drains. They were up to 5-6 meters deep and it intercepted water bearing sands. The East Coast Main Line was electrified through here in 1986 and 1987, and single track cantilever OLE stanchions installed. A sheep hole wall was and embankment regrade was undertaken at the high mileage end, which is related to instability at the site. So at the time, it was just related to an embankment, local embankment failure, but it was actually linked to the main landslide failure. And there were other local subsidence issues that occurred on the site associated with movement, and coal collapsed in 2002-2003 that required grouting and an additional drainage system constructed in 2003, which led to another ground investigation, quite an extensive one across the site. And then in 2015, further ground investigation was undertaken, cost share between Durham Council and Network Rail as movements increased. And then we scoped and procured, working with Story Network Rail, further ground investigation in 2017, as there was a real push to try and get this site sorted. And the OLE were replaced with twin track cantilevers, or most of them, in 2019. So the interesting thing for me, but maybe not less so for you guys possibly, is we need to find out what the problem is. We need to define the problem. So the design tends to be the easy bit, but you need to define exactly what the problem is before you can fix it. So the published geology across the site showed alluvium really along the banks the River Browney at the toe of the hillside. Then it was shown glacial fluvial deposits, sand and gravels, which is the pink area, and some glacial till, which is the blue, and all overlying middle, Pennine middle coal measures. So what we did, we went back to the beginning. So each time a ground investigation had been undertaken, it seemed to be done in isolation. But by the time we got involved, there was such a wealth of archive information that we just had to put everything together to really fully sort of delve into what was going on. So we went back to even 1871 ground investigations which were undertaken for the construction of the railway embankment to start with, and put everything together. So this is the low mileage southern end of the site, and that's the still sharing. There we go. And that's the high mileage northern half of the site.
Still in here.
Sorry, it's flicker. The screen's flickering here. So there were 320. I think it's 320, 325 exploratory holes were mapped and put on the plan. And it's flickering again. This is some of the information from 1871 that we found, and I had the pointer. You can pick out there's some breaks in slope on the hillside. The embankment is shown in the location where it's planned to go, and you can see from that, and looking at the ground conditions they described, matches very well with what we encountered and what we found during subsequent investigations. And it was clear, looking at these profiles, that they had shallow instability across the site before the embankment was constructed. And this is from the late 60s, early 70s. Some cross sections from some exploratory holes that were put down through the high sections of the embankment across the site. And you won't be able to read this, but there's basically this dotted line through here defines where the base of, above that line we found evidence of timbers, boulders, stones, things that shouldn't have naturally been there at that site. So that's a good indication of how much excavation they did below original ground level to find a decent formation to form the embankment. And there's a reason for that, which we'll come to. That's a nice glorified shot of surface laid over the holes. So it's quite noticeable. There's a lot more GI at the southern end of the site as you come out of Burney Gill Tunnel heading north, because that's where the main trap faults are as you come out and strain from the tunnel. And it's also the area with the highest movement. So a lot of the previous investigations focused at this end. So these are geological sections that we plotted up. And so to start with, we want to try and understand what the stratum are across the site. And you can see what we have is typical in this area. We call it a tripartite system. So we have laminated clays, so glacial lacustrine deposits, which is the dark green at the top, overlying glacial till, overlying glacial sands and gravels, which is the yellow. And then it repeats again where we have laminated clays, which we just call it the lowest section, lower laminated clays, onto the garish blue colour there, which is lower glacial till, and then onto the coal measures below. So we have laminated clays, glacial tills, sands, lower laminated clays, and then higher strength glacial till lower down. So it repeats. And if you can see, the main water bearing strata is the sands and gravels, and they daylight out of the slope exactly where the embankment was constructed. So you can see they're always going to have problems locating the embankment there. So you can just imagine the problems they had. There's the same with the deep drainage that was constructed in the 80s when when they excavated down at depth. They had problems with collapses. There's a lot of water down there. So And you can see it's sub horizontal. So across the site, this repeats and is pretty consistent across from low mileage to high mileage. And this is just further to the north, high mileage. It's slightly less exploratory holes, but we have the same sequence where we have the upper laminated clays, glacial till sands, laminated clays again, and then glacial till. And the thing to remember is the laminated clays have much reduced stiffness horizontally than they do vertically, and therefore they're prone to slipping along the laminations. And interpretation of the slip surfaces. So in the 70s, there was a lot of information. They put alkaline tubes down, which are a sort of early form of slip indicator within the embankments itself, which was crucial for us because it's easy from 2003, 2015 investigations. Access was quite difficult to get onto the East Coast Main Line as it is now. So there was a lot of investigation done either side of the embankment, and that focused attention away from the embankment. But the information from the 60s and 70s, there was a lot of slip indicators there, which gave us a lot of information. So slope movement indicators were the alkaline tubes in the 70s. Inclinometer tubes installed in the boreholes in 2003 and 2015. We installed more inclinometers in 2017 and some shape accelerators within the boreholes, purely because we found out that when your standard incline tubes they bend, once they get so far, you can't put an instrument down, so you don't know what's happening below that. And we knew that there were multiple shear surfaces, so it's not just one in one certain shear surface. So within some of the holes, we knew there'd be more than one. So we need to make sure that we can pick up movement for several shear surfaces. And then the other one was very, very clear to us was the drainage system. There are 3 or 4 UTXs that cross underneath the embankment, taking drainage from the upper hillside down to the river, and the collapses on the UT axis that needed a grouting up that caused the difficulties on the East Coast Main Line in 2002 and 2003, and also damage from drainage surveys, damage to UTXs that were still functioning. You could pick up where displacements were, so that was again a very good indicator for us of where the slip surfaces were. And again, which I'll show you the photos, slope movement indicators at track level over overhead line equipment, displacement on the tracks. You can when you go up and walk along the cess, you can pick up where you can visualize where some of the track faults are and identify where the failure zones are. Geomorphological mapping was crucial. Obviously, the topography, you saw the picture showing the slope gradients across the site. That basically gives a very good indicator of where the landslides are, and vegetation. So if there's hydro, if there's water zones and vegetation that likes water through there, then we can identify where there's seepages. And from that, we could identify where the shear surfaces were and plot where the landslides were. So originally, there was some assumptions that it was one big landslide that was affecting the site, which is why some of the investigation holes that we put down in 2017 were there to prove that there weren't slip surfaces there rather than that there were. So we moved things around to just positively identify negative, really. So as you can see on this, we've got a more rotational failure through the upper laminated clay on the steeper hillside at the low mileage end, which is this section, and then more translational as you go further towards a high mileage part of the site on the upper hillside, where it flattens off. And then the landslide, which we call landslide 1, which affects the East Coast Main Line, is in the cess on the downside and goes all the way down to the river, and is rotational at the top and impacts the toe of the embankment slope. and then runs through the laminated clays, the lower laminated clay, translationally down towards the river. And again, this is for the high mileage. At the high mileage end, the glacial till tends to be slightly shallower, so the profile of the landslide changes slightly, and it's running along the interface between the base of the laminated clays, the lower laminated clays, and the top of the glacial till, the lower glacial till, which is relatively high strength. And then we produce these models, and you can see from some of these the relative size of the embankment versus the slope, the whole hillside. It's pretty apparent that it's quite a significant structure on the hillside. So it was always, the thought was that it was always controlling the failure. So really, landslide 1, which is the focus of the remedial works, is to restrict movement and stop movement of the main landslide and impacting the embankment down to the river. And then we've done some further works on the upper hillside to protect the network rail boundary and the drainage systems in the upper hillside. And also this shows quite clearly the yellow zone, showing where the water-bearing sands and gravels would have come into the base of the embankment, and the sort of paler purple there is cohesive embankment fill, and the upper sections more the actual granular embankment fill. So they put in quite a lot of granular cohesive fill at the base there to try and stop up that water sinking to form a foundation from which to build the embankment. And these are the pictures. I'll rattle through fairly quickly. You might be able to just pick up the backscarp of landslide 1 going in the downcess all the way through. You can see the lumps and bumps in the upper hillside where it's slightly steeper. So this here is the failure in the 1960s that pushed out onto pushed the network rail boundary fence over, but didn't impact the track. And then we've got more lumps and bumps on the shallower slope below, which is a function of failures daylighting within the lower hillside, as well as construction waste from the original embankment construction based on boreholes. And these are some of the indicators of movement and understanding where slips were and where they weren't. So you can see Overley 7, one of the older single track cantilevers, is much higher than Overley 8 on the upside, and the rotation there. So you can see that that's fairly stable, and this just keeps dropping down. So there's a good indicator of where the backscarp is, and you can see the backscarp through there, and it dips round and down and changes course. And then we've got some local instability on the embankment slope, which is fairly steep on the downside. Sorry, on the upside. And this is just further towards a high mileage. Again, you can see Overley 9 and 10, much higher on 9, much lower on 10. You can see where the catenaries are changing on the Overley stanchions as it keeps getting adjusted to maintain the clearances. And clearly, you can see there's no the very limited ballast shoulder and limited cess. So part of the remedial works were to reinstate the ballast shoulder and cess and put a safe cess walkway along there. But that's purely a function of the amount of movement that's happened, which I'll come to in a bit. Again, more minor scarps, and this happens to be the platform where some grouting works were undertaken from the previous UTX failure. This is at the northern end, so the regraded embankment that was undertaken in the 80s, and this is a sheet pile wall, which has actually been very helpful to the scheme works we've undertaken recently, because this is at the northern end of the failure and helps soften the track faults at the high mileage end. And this is talking about rotational failure at the top. So this is a breaking slope in the lower slope below the embankment slope. And this is where rotationally the embankment would want to fail up and through as it starts stressing that area, that it causes the shear surface to go translationally down to the river. And these are seepages where the water's been coming out where there have been some shear surfaces. And again, that's just looking at the other side. And the river's playing its part. It's eroding the toe, so we get bank instability. All this is unstable through here. So what happens is the landslide's feeding the river's taking it away. So the works involve doing some soft engineering to prevent erosion of the riverbank at the toe. And this is only 3 at the low mileage end. There's Gill tunnel, and it's just pushing and just slightly in the upper failure zone of landslide 1, and also getting pushed from the upper failure at the steepen end of the low mileage end. So it's quite complex through here, and this is with the sun in the right at the right angle. You can see the backscarp very clearly, and it's a good indicator that the embankment is controlling the backscarp because it's largely parallel to the East Coast Main Line, to the tracks. And again, this is the backscarp around OLE7, going off into the distance. This initially, I think, was thought to be some sort of drainage ditch or a channel when the sidings were removed. But this is why we put extra bore holes in to check where the slip surfaces were. And that, again, is the backscarp. So that's the level of the embankment previously, and it's dropped down to there. And then there's all this ballast that's been put on over the years to bring the tracks back up, push them back up slope again. And this is at the high mileage end as that backscarp travels back through and crosses over close to where the sheep hole is on the other side, on the upside. These are where there's stretch and tension in the signal cables as it's crossing over. And that's just the toe bit, 66 failure, which I mentioned before. And this is a very cartoonish picture, but we've got the middle glacial sands, which are feeding water into the base of the embankment, which is causing increased border pressures, which is driving the failure. Got a steeper upper slope, shallower lower slope, but largely the East Coast Main Line's impacted by the main landslide 1, which is a compound landslide, and we've got a rotational landslide, but landslide 2 above, where it's steeper, and some drainage in the upper hillside. And this is just an indication of a plan of where the backscarps and the toe of each of the failures are. So landslide 2 is less of an issue generally, but it's impacting the drainage on that upper hillside, which helps prevent increased border pressures getting underneath the embankments and driving failure and movement on landslide 1. And typically landslide 1, as you can see, the backscarp runs parallel to the East Coast Main Line, and the toe of which is within the riverbed. And in certain areas when it's fairly dry, you can see where the feature is. And the East Coast Main Line shows track faults locally here, but they're not that significant. They're not that severe because this sheep pile will help sort of shield and soften that transition. Whereas at the low mileage end, where it crosses, as it's just to the north of Gill tunnel, it's quite a sharp, pronounced break. So a lot of the track faults historically have been in this area, and so where the embankment's steeper and there's some side shears just slightly further north. So that's what it looks like with some very simple circles around it. So landslide 1, East Coast Main Line down to the river, and landslide 2 above. And again, I'll carry on with that as I've shown before. Displacement rates. So from the inclinometers, slope monitoring arrays, topographical surveys, displacement sensors within some of the manhole chambers, we can get an indication of rate of movement. So in landslide 1, just south of the site, there's a lot of movement. It's about 100 to 400 millimeters per year, or has been up to 2022. The main body, the middle section of landslide 1, movements are generally around 20 to 60 millimeters per year. And they vary on the high mileage end, around 35 to 50, sometimes 80 millimeters per year. And then on the upper hillside, it's much much slower movement. So, but generally about 5 to 15 mil, and then just slightly higher at the southern end. And in recent years, it's picked up quite a lot just at the very southern end. So we've done some stabilisation works there as part of this scheme to try to improve that. And that's that's that. So this is just a chart showing the same thing. So when the overheads went in 86, we got some very definitive as-built survey information, and that was repeated in 2003 and again in 2017. So we can estimate average movements per year. And what this shows is that from 86 to 2003, we were generally getting limited vertical movement and around 10 to 20 mil horizontal movement across the site. But then when you look at 2003 to 2017, it picks up significantly. So the low mileage end, we're getting around 50 to 60 mil, upwards of millimeters per year vertically, and not dissimilar horizontally. And at the middle to higher mileage end, it's around up to 40 and up to 30 equivalent. So what that shows is rainfall events are much more significant and movement rates increase, which is why there was more work and more focused on the site. And this just gives an indication. Rainfall is important, but it depends on what time of year rainfall happens as to the rate of movement. So there's a lot of rainfall in winter and spring. We get an increase in movement. So this is weekly displacement of some of the inclinometer sensors that we've got across the site. But when that same rainfall happens in summer and autumn, which is the rainfall down here, the movements are much reduced. So as you'd expect, so there is a seasonal effect to rate of movement across the site. And groundwater, I'll go over this fairly quickly. Groundwater influence. So there's main groundwater table, which is controlled by the glacial sands and gravels, and it generally follows the lower slope down towards the river. And then we've got a perch water, which is under draining into the glacial sands and gravels. So the key driver for landslide one is the main groundwater table within the sands and gravels, which feeds water into the base of the embankment. And it's just some pictures of seepages across the site, which shows how groundwater is, as you'd expect, fairly near surface for the most part. This is again one of the drains that we had to fix. That's been like that for a number of years, so by the time that got sorted out. And this is this year.
Yeah.
There you
go. So in terms of the works, as Andy's alluded to, we've got landside 1, landside 2. There was significant temporary works required. What you can see on the plan at the moment is the permanent works plan. In the very small, I don't know how easy you can see. These are all our CHS piles, which there are 2 rows on the upper, like a double row and a single row there, and then the lower row, as we call 1A, 1B, as they pile row 1 and 2 move along there. This is how we attempted to stabilise the embankment. There was 529 piles, which Ed will go into more detail on shortly. They are spread across the site, and then you've got the upper landside 2, some sheet piles in here. These are trees. Maybe skip over that part, but at the moment you will see the site. It looks if anybody passes it on the train, it just looks like a muddy field at the moment. It's a good thing. We've finished the works. What we have done is installed a regraded section of the embankment and the CHS walkway. So if it is required to walk along that, as you couldn't do previously because it was a complete drop off almost next to the sleeper ends. This is a typical cross section. So as I mentioned, you've got from landside 2, you've got sheet piles in here, a drainage run that runs to the length of Browney Curve, your regrade, which we've got benched in here, and then you're up, I think up to 22 metre long, 25, sorry, piles in there, and then lower to stabilise the embankment. Keep moving quickly. It's just temporary works. What we had to, one of the challenges when before we started on site, the local authority undertook some stabilisation works to the road there. They installed their own contiguous pile wall, to not necessarily to the best of our opinion. This meant our temporary works through this area were more significant. This is onto, you've got Bernigal Tunnel just here. See it from my perspective on the TV, I think it's still lower looking down the road. So that ultimately impacts on the areas we need to come through from a work perspective. This is a route view aerial image from February 2022. Browney Curve is sort of to the bottom right of the photo that you can see. The only access to and from site was through this area. The photo, you can see the soil that's just in front of the wall. That should have been continuous level with the wall that the local authority installed. Instead, that material slipped down the embankment towards the river. As you can see, the movement of it just from the imagery there. It ultimately required significant temporary works to facilitate access to the site. As slide says, it's the only feasible way. The amount of plant materials, machinery that had to come to site, it wasn't possible to come through the tunnel at the sewage access point to the north. Couldn't come from over the railway. She'd have to build a significantly temporary bridge. So this was the only way in and out of site. That's just another view from there. And as I mentioned, the topsoil that put on there should have continued all the way along this pile cap. You can see it's already dropped. I think that was January 2023, just before just as we were developing the pricing and the final temporary works and AFCs for this project. So we've got some further images of that. So we ultimately renamed the site with 3 landslides. Landslide 3 being the temporary works area that we had to get through to get to the main works area of landslide 1, and then landslide 2, which is a lesser problem but still a problem that feeds into the overall Browney Curve site. So the drawing on screen is the temporary works required to provide the access to and from sites. You've got your haul road in the middle, your access road, and then 2 rows of sheet piles on the upper platform and lower platform, which will stabilise that area. Sort of where my hand is where the indicative position of the we call it Durham's wall and the road itself, and then I think that's your failure line into Andy. Yeah,
the walls around where borehole 104 is.
Right, yeah. So the materials ultimately going down there. We've installed 2 rows of sheet piles in here to stabilise the road so we can bring all the material, plant, equipment, etc. In and out of site. It's just got a sort of a top-down view of the access road in and out of site, which is our north-east art installation of the year. These are the sheets as we're going in. Ultimately, not all to depth as the time the photo is taken. Some went in easily, more easily than others. Ultimately, they are all now in the ground. These were massive to access site and stabilise landside 3 to allow us to access an egress site. and were critical to the success of the job. This is just some data. So the landside 3 itself was monitored since we kind of continued monitoring on site. The hashed line around the 5th of December 2023 on the graph you can see is once all of the sheet piles were installed. You can see the movement rates accelerate from the point we start monitoring, the point the sheet piles are all installed. Just there or thereabouts flat lines, you are cumulative displacement in millimeters, so you're not talking masses after the hash line there. The bottom is just rainfall.
Yeah.
So you see that. As I mentioned, access to and from site. So you've got the bottom of the photo. You enter site, and then we worked our way in terms of the temporary works. We built piling mats all the way along the bottom, and then built them all the way back out on the top. And the same for the permanent works when we're installing the piles. We worked all the way along the bottom and all the way on the top. That's a lovely drawing one of the engineers drew this time. I'll pass you over to Ed now.
So, challenges of the railway. Ultimately, it's the East Coast Main Line, directly above us. The key problem statement driver for the scheme was we must keep it up at line speed. Significant delay minutes if we put a speed on was sort of prohibited. So how do we go about doing that? So to ensure that we understood what the track was doing and ensure we could meet traditionally use the service standards, when movement occurs, you stop works. Naturally, you're doing something that's not shouldn't be causing movement. Obviously, for our scenario, site's moving, so we have to understand what the movement is. Is it comfortable movement or is it uncomfortable? So to ensure we had a picture of what was understood and ensure we had the confidence to give all the stakeholders to run at line speed. It's a 90 mile an hour piece of track. We put total stations running 365. They were measuring the whole site every 2 hours, just over 6 million pieces of data measured, processed, and spat out. The graph on the right hand side is ultimately one of the outputs. So that's showing one of the OLE stanchions relative to the target. So the bottom lines, the stanchion was dropping with time because we can't do anything into intervention. The other graph, the higher level piece of the graph is when the tampers were involved. So we had Gary's team, delivery coming out periodically for 6 weeks and tamping the track to keep us up to the baseline. So you can see over time when there's movement. So we started main piling mat construction. We knew would disturb the site by the very nature. You've got to move weight across the site to get a piling mat suitable for a piling plant. So you can see the site starts dropping. That's when the equipment also went on. So the historic picture would be similar with some of the older data sets. But you can see when the tamp lifts it back up and then it drops back down. Something else on site, Andy's already touched on it. The inclinometers presented another layer of data. So we had pure 3D measurement of track. We had inclinometer data, what was getting both automated and manual, confirmed movement in the boreholes. We had a weather station confirming rainfall to get us that pre-1. And then we also had the likes of the measurement tray came through, rave data, what's been relatively new for NetRail to use, and then physical boots on ground surveys as well to give us some confidence in what is occurring on site. So this is the sort of output of the site. This is a topo file, what was a live portal. Anybody could access it across the whole NetRail sort of ecosystem. Anybody could access it with the right request. This also allowed us to have weekly meetings, have targeted interventions, and also just decide, do we need to get a tamp in early or can we wait? This is showing the horizontal displacement. So obviously as the hillside rotating, track's trying to move sort of down slope ultimately. So only 12 would be the up line versus the down line. And then the other graph is the vertical. What you can see is a lot more excessive. Blue lines, one of the stanchions again. So the challenge we also had to, even though some of the stanchions were new pile cantilevers put in the 2017. 2019, sorry, they were getting to their operational tolerances. So they were designed to have adjustment. Well, we couldn't adjust them as easily as we could adjust the track. So it's a map that as well. Similar sort of bits of site, you can see different areas of different levels of movement. Only 9's further north, so it's further to the sheet piles. Slow the movement down. And then that's just a element of how the track is moving in each leg, the time, the vertical displacement, etc. So
that's a long low mileage to high mileage, so it just shows how much movement you can pick up. You can pick up where the line picks up at the low mileage end. So for the
that's the main twist fault in that area,
Yeah.
hence why you've got the most movement.
so it's basically an indication of exactly the extent of where the landslide's impacting cracks, which helped us understand as the piling was coming through. You could almost see the bow wave and the movements as you're piling coming along the particularly the upper pile row, the pile row one. So we have very good control over exactly what was happening, which was obviously integral to the work. So
ultimately, this project managed to stay without speed. We managed to keep the railway in operation. Yes, we had to increase some of the intervention regimes. It was going for the success of the scheme. I'll skip through these because I appreciate we're talking a bit about time. So in terms of some photos of the site, you've already seen that photo. This is a bit later in 2022. So this is when I first visited the site. I'm stood by the tunnel looking down the site, and it clearly shows the pronounced features. The timber squares are all the boreholes, and you can distinctly see the troughing up here when it's drooped. It's all the movement. This is the upsess embankment shoulder. This is where majority of the East Coast Main Line's SCT equipment was located. There is a troughing ruin here. What presented some challenges with the scheme. You can also see some of the stanchions at this point have been left in. They were to give good baseline movement, keep a constant trend of something that's not moving on site or being interfaced ultimately. This was Durham's wall. For context, that photo was taken about 2 months after that fence went up, and you can see at this point the fence is already retaining material, just to show you the extent of the landslide features. So, touching back on what Tom was saying regarding access, the site itself, we had to come through this corridor. We looked at even going across the river, Bailey Bridge. Problem is historic England Country Park. That was out of the question. To the north, your biggest bridge could get, if you're lucky, a 20-ton machine through. We need a 100-ton pilot into site, so that discounted down. That's the site in the April. So we moved in the April. We got a bit of early contractor engagement piece to remove the bats. So this embankment was littered with quite a few bat roosting potential features. So we got a bat license and moved them to the wider site. So that's now out of the site from a college point of view. So we will not the works. So when we got committed to start, the works will continue and be as efficient as possible. You can also see on that photo, it's quite telling how fresh the ballast is. Ballast was getting dropped at peak every 12 weeks ultimately. June, CHS was procured. So the CHS itself, we're talking, we needed just shy of 30,000 tonnes of steel reinforcement. Our original plan was to go to Turkey. You may remember in the June of this, or a bit earlier in the February of this year, 23, there was quite a significant earthquake in Turkey, what turned that supply chain quite quickly. Something as a business we've done before is we've looked at using reclaimed steel. So all the site was based on a mixture of CHS reinforcement. So that's the main reinforcement for the pile. The design was based on 610 reinforcement across the site as a generic design. In the end, I think we had everything from about 540 at 14 mil, right up to 700-ish.
512s up to yes, yeah.
At 30 of them. Yeah. So we had to take a wide stock of supply across the country. There's a supplier who sort of speculates on this. It's all reclaimed oil and gas stock. This started quite a big logistics cycle, as you can imagine. It's not all the right length. Something we've done one of the restricted access jobs we've done before, and something we've done with Sheffield Uni, is got a design together what means we can put a threaded connection on CHS piles with a weld, single pass weld. That allows the piles to be threaded together on site and get to site a lot easier. September comes and we actually mobilise the site. So this is the field to the sort of side of the road. At the time, we were mobilising. This is a floodplain as well, just to present another challenge. Our compound is a floodplain. The bund provided some flood protection and a frat permit from the EA. And that photo shows why we put the bund in. This is the same photo, just taken a couple of days before, a week before Tom's photo with the sheets going in. But this is the main access road coming through where the roll was sat. 12-metre sheets. One of the challenges we had, the slip plane's about 8-9 metres down.
Yeah.
On
landside 3, yeah.
On landside 3. Yeah. The very nature of being 8 to 9 metres down means you need 12-metre sheets. 12-metre sheets with a Movax isn't the easiest of things. Traditionally, we'd go down a leader rig route. It's a lot bigger, a lot more powerful, more designed for that sort of size. And piles, so you have to have quite significant weight piles as well, for the very nature. The problem is because the site was so unstable and it was moving, we couldn't get the temporary works to work, so we had to back ourselves using excavator amount of Movaxes to get them in. That's a photo in December. At this point, we started to progress into the main wider field, and that's taken a step. You can see here the back scarp as well. On the side. And that's also December. That was the same day site. And you can see at this point, we're hammering those to depth. It take time, but ultimately protected this sterile corridor. For the amount of material, but over 100,000 tonne of material to come into site. We had 12,000 cubic concrete to come into site. Those sort of vehicle movements had to be on a stable road formation base. CHS started coming into site in the January. The compound started to look a bit fuller at this point. And you can see in the far right hand corner, the site getting built. That's a better photo of the site and the significant temporary works. Part of the need for the piling rig itself was about 6.5 metres wide. It needs a crane, what's about 6 metres wide. It also needs a bit of capacity. So the mats themselves were 14 metres wide. Given the nature of the landslide, we couldn't naturally dig down because you'd end up undermining the railway. So all the embankment fills, the embankment would be temporary works embankments ultimately for the piling operations to keep the cut to a minimum in terms of stability. Something also to know on here, the highest risk part of site is this piece here. This was deliberately left till just in time to ensure that any movement piles below it. So where the rig sat, this is the piling rig that we delivered to site. That's the first piling rig we worked on, and then we worked away to the right hand corner and came back along the site. You'll also see there's a bit of temporary berm built when we came to excavation of this mat. They had quite a big significant water bucket. So to prevent that, we built some embankment early. That's the site when piling commenced. So you've got a leader rig, what's physically driving a 80 casing to depth. So that's going to drive casing to 20 metres. The crane's lifting the CHS in, and the rig on the right hand side is a welding operation. So that screws the CHS together. It gets welded and then lifted into place. The challenges of the site with the sand lens below the upper glacial tip, like the casing was up across the site, casing was to full depth. The piling operation would be a lot quicker if we could have cased not to full depth, but the very nature of you couldn't get a stable bore when you were down at sort of 20 metres plus, your bore started not being stable, so you couldn't get your CHS and you couldn't get your concrete in. So we had to case to full depth. What presented some challenges for our piling contractor Keller, but we got there in the end ultimately. This is the site in April, and you can see we've worked our way along here. You can just see the end point of the piles, part of the Form 1 design optimization. We looked at having a capping beam, but given the nature of Andy's team ultimately worked through and ensured that the capping beam wasn't needed for them, both significant time and cost saving across the site. It also means the site can be reinstated without the need to see the sort of site, the piles. The upper slope, you can see at this point, is ready for sheet piling to commence. So we had about 6,000 metres of sheet, linear metres of sheet piles going in this upper slope to protect from landslide 2. What was done. bit later on, and some counterfault drainage across the site. Part of the site, same as we're doing tonight, we had quite a lot of interest. Ourselves, LCE, emails, teams, but in the site itself. It's surprising the amount of people like yourself and you walked in here, you've been involved in the scheme. There's quite a lot of the community who've been involved in the scheme by their own nature. This is July, and you can see in the upper slope, we're now sheet piling the upper slope as well. So this point was probably one of the most high risk times for the site. We had piles going on in the lower slope, we had piles in the upper slope. At this point, we also went to working 24/7 to make sure that risk across the site. This is a photo in the September where we start piling finishes in the September at this point. We've already started to reinstate the site. You can see the regrade berm being built along this front face. That's the site in December. So you can see the tiered approach to building the embankment regrade. This had just under 30,000 tonne of filling in its own entity. Some of the wider network would have that as its own scheme in its own right. That's to ensure that the slacking of the side slope and also compliance test walkway could be built. You can see at this point we've also moved to a more smaller compound setup. That's the February where the site progresses, and you can see the regrades sort of come along there. Something that we probably haven't shown on here is pre-September, there was quite a significant piece of work by the signalling teams to move their assets from the up embankment to the downside, what included a new UTX and also relaying and one asking to find the cables once in the cess. Because clearly us providing to do works in here prevented significant risks to those assets that were buried. It's quite a challenge, but it was overcome. In terms of carbon, and some of the carbon credentials, the biggest saving was the non-prime steel, just under 8,000 tonnes, just over 8,000 tonnes of carbon saved, not milling prime steel. Quite a lot of materials supplied locally. Thankfully, we were lucky there was a local quarry to keep the vehicle movements down, and then we see the carbon from the pile being emitted. We shall open the floor to questions. I think everyone online can. There's any questions in the chat?
I'll just have a look.
Oh, that was
Very good, thank you. Anything any questions on the chat?
In the chat.
Please go away.
So from the slope failure point of view, you mentioned there was a rotational failure on the top slope.
Yep.
And there's a compound failure on the.
So the compound failure is where you have a failure mechanism that isn't just one type. So it's a compound failure because it's rotational at the top and then goes to translational along the laminations parallel with the surface. So the whole landslide, each landslide, particularly landslide one is a compound landslide because it's rotational at the top and then it goes translational lower down. So the part of the regrade is to try to prevent that upper rotational failure daylighting above the upper row of piles that have been put in. So without that, there's a risk, and the embankment side slope is pretty steep and unstable as well. So it's trying to manage two risks on that one landslide. So
sure.
I've got a question, if that's all right. Great stuff, actually. And you know, cast my mind back to when I used to be out there in the 90s and being in maintain. I can now I've got a better understanding of that. And I can see your last stage, sort of 1, 2, and 3. They're all to the north of Burnacle Tunnel. So a two-part question really. Has the structure, the tunnel itself, been affected by this movement? And in the future, is there any risk that, again, I can see what your works have arrested that movement in that problem area where we used to get the track quality faults. Is there any risk that natural movement might move towards the structure?
So the embankment pretty much goes into grade tunnel. You're going to put on the other side. Right at the start, when the movement starts picking up, it's the first thing the structure needs to ask. Can you monitor that structure?
Yeah.
Can you ensure it's not moving? And we've demonstrated with the data sets that it doesn't really like
do you want to go to the plan?
showing the which buildings you got.
Oh, that's the new photo. There you go. Go back. Right. So at the low mileage end, they've got Bendigo Tunnel in here.
Yeah.
What we've done is pulled the piles as far to the portal as we can. The risk to here is because of the topography there, the risk to the tunnel is very, very minimal. There is a risk that this could come round and impact the tunnel portal, which is why we've extended Pole 01 as far south as we reasonably can to mitigate that risk. So and you'll notice from the pile locations, they're quite varied, and that's because during the temporary works assessment, obviously putting piling rigs on an active landslide in the railway at the top of it isn't a usual approach. So we moved the locations of the piles to suit the temporary work because we need to balance the stability of the site to make sure all the work method is worse.
Yeah, in my simplistic make, not obviously, tracking. I think you put a wall in, stop some things going downhill. It's gonna push out the other edges. But you're seeing that it shouldn't affect the structure.
So normally on this we've designed to sort of ULS ultimate limit state, but because of the railway, stiffness was critical really. So it's understanding how much movement that the hillside's going to see in response to certain changes in to rail loading and things like that. So it's really focused on stiffness and the whole sections are specific in certain areas to manage areas which are stiffer and less.
Yeah, got you. Understand. Yeah, super. Thanks.
Right, I've got one. I left the industry in 2009. I've had a 50 odd years experience of this site, and the track was degrading with all the tamping. The bottom of the sleepers were becoming rounded, and the fastenings were always coming out. So has the track been replaced?
There's a track renewal plan for this control period. I believe it's year 3 and year 4. As part of that, they'll be undertaking OLE modifications as well. I think it's as a package of works. The earthwork, like to say, has been fixed. It's been stabilised, and then instead of them continuously tamping, adding ballast, it will be a full track renewal undertaken by, I think it's CRSA, you may know.
Is it your intention to take any of the ballast away? Because there must be about. Yes,
A lot of it's buried.
It's back to formation. Maybe trying to change the drainage profile as well.
So since 1986, the tracks have been lifted cumulatively up to about 1.5 meters, and then sideways about 2 meters. So they have incremental. They have in total, but if you work out, probably since when it was constructed, there's probably a good 2-3 meters plus of ballast in certain sections across that.
Teamed up gave a good indication of how much slippage that had been to my short time.
You can see it in, I think, at least 2 of the photos there, how much ballast had dropped downside. And the key problem for us, as Ed alluded to, within the inside of the curve on the upside are all the S&T cables and the shopping routes, and that over time has become buried. And in order for us to undertake the regrade, those cables either need to be dug out or cut at one end, cut the other end, and relayed on the outside of the curve. And as a project, we've taken something on, engaged the maintenance teams, engaged the third party, because you've got a fibre optic cable in there as well. Install the UTX to the north, so where they do historically cross the railway, just north of the tunnel, they now carry on down on the downside and then cross further down, because you can then maintain them, and they're not on the inside of the tunnel. Ultimately, you're not going to be dropping ballast to the extent of historically has been done, but you've made an asset for at least 2 or 3 different asset owners a lot easier to maintain and access.
There's a question online. Ben Brooks has asked, you delivered without a requirement for any TSRs during the pylon, which was a fantastic achievement. What was the original assumption with respect to safety speeds during the works?
We designed an ESR as part of our works requirement. The request from the group directors was that we don't implement a TSR as part of the works. I think ultimately we would have preferred to. You have that safety, call it safety blanket, but with the amount of monitoring, both got hourly assets, geotech assets, track assets being monitored 24/7. The alert system that were fed into root control as well. There was a level of confidence, a level of assurance there that if something did go awry, the data was there and the alerts were in place to react to it immediately.
And we had weekly meetings, so all the team with tracking there was constant communication, which was critical. Without that, I think we would have struggled. But that communication and constant going through the monitoring, talking to track team and ensuring that the maintenance interventions were at the right time and they were in charge of when they were comfortable, when they weren't, and the look aheads were crucial. Really. So.
I think, I don't know if you did say it, but it was said multiple times on monitoring calls. Failures somewhere like Browney don't happen overnight. They happen slowly, but you almost can see them coming through the data. So if the data was showing increased movement above sort of intervention, or kind of got to a point where within the monitoring plan, if you need to go out and intervene, there will be mobilisation calls with the TME, with the relevant maintenance teams, to go out and undertake additional surveys just to verify, or go out and intervene back additional TAMPs that were required, ad hoc to the 6 weekly TAMPs that we agreed on to projects.
We always knew the piling works, the construction works were going to accelerate movement. So there was a background average movement per year, and it was nailed on. We always knew the works were going to increase the rate of movement. So it's just capturing that and understanding the reasons behind certain things, so that we could have predict what was happening ahead of time was critical to keeping the railway operation safe. So, and I did a good job of that. So.
Well done. Another question.
One quickly.
Walter?
So with all the looks done, any plans to revisit in future years, or is it?
So part of the, so part of the site and completion installed 14 kilometres to demonstrate success. The idea is that you want to get monitored to ensure that we understand the site for long enough belief. We're also doing manual surveying site the first year. Longer term, I think this is track window to go through. I should have done before. Yeah. So I should be protected. 120 years with the design line.
Yeah. So it's a deflection piece. So the design for very high groundwater changes, they're designed for sort of, I indicated that the drainage system in the upper slope controls rate of movement as well as obviously what falls out of the sky. So if groundwater levels were to increase significantly because the drainage system failed, then the piles could cope with that, but they result in a bit of deflection. But the drainage system is less likely to get impacted because the main reasons for blockage were to do with the slip surfaces intercepting the UTXs and causing blockages and shearing. So by stopping the slope movement lower down, it should prevent the UTXs from getting blocked. So it's a maintenance piece with the drainage, and the first sort of this year the sort of piles bedding in to the new equilibrium. But from the monitoring we've done and what we've monitored in the last few months, it's flatlined. So we might get a little bit of a response if we have some heavy rainfall, but anticipate that to be very, very minimal. So it's looking, yeah, results are looking pretty positive in those.
Okay, got another question. Does Durham County Council have any more road stabilisation works planned?
They have a design available.
Shell.
That's how I'll leave it. In that sense, they have a design available if there's any subsequent movement or the road starts showing signs of movement. There's a design available to be implemented. But their road is not, obviously a road is a lot more tolerance for deflections compared to a railway. So they can deal with a lot more. So they have something available. Personally, I can't see it being implemented. We've left our sheet piles in, provide a betterment. We don't provide the sheet piles on all about temporary works and providing access, but they do provide a betterment to slowing down movement across that side. So
The sheet piles for landslide 3, which is an extension of landslide 1, were really designed as an observational approach. We couldn't really get the sheets in deep enough to get a fully compliant Eurocode design. So it's about just slowing things down to enable access. But the movement in front of the concrete pole wall adjacent to the road, the poles were installed fine, and the wall's not showing any deflection. So I think with the sheet staying in, unless there's a significant change, I think you know it's a visual impact piece at the moment, that wall. So rather than anything else, but yeah, we're yet to see what happens. So.
I'm just thinking from memory, because I've done quite a lot of work on here, track-wise and what have you over the years. Was the overhead and the track moving at different rates? Because we put the TTC in a few years ago because we lost the capability of returning the overheads back to a compliant position at that point. And we actually couldn't put a speed on then, because if we put a speed on, then we wouldn't have thrown the pan across enough, which would have caused more of a likelihood of the pan coming off.
Good question. So it's quite complex on it. So in the middle of the site, you've got some of the, let's go back to the single track cantilevers and the high mileage end. They're the single track cantilevers are the ones that are supporting the overheads. That they're both sat within landslide 1. So obviously they're not moving now, but pre-works, they were moving at the same rate as the tracks were.
Yeah.
But as we come further south, some of the on the downside, so upslope, some of the stanchions were right at the interface of where the backscarp was. So they were bounded about 1.5 meters to 3 meters down. Some of them on 610 CHS foundations. And the presence of those foundations deflected the backscarp. So some of the stanchions on the other side, they were founded below the backscarp, but the passive ground in front was moving away from them. So they were leaning, but they weren't settling.
Right.
And others were fully behind the backscarp, so they weren't moving at all. So
Right.
so you're going along there. Some are moving, some are dropping and moving sideways,
Yeah.
and some are just going with the track. So I can understand that.
Yeah.
It's
I remember when we were
quite
trying to do
difficult.
that, it never seemed to make sense why the track was moving away, but the overheads weren't moving at the same rate of the track, and then we're trying to put both of them back together at the same time.
No, it must have been quite a difficult job.
Okay. Another question. This off Phil Watters, and he said, not question, no, not really a question, more of a statement. The moving of the signaling cables from the inner radius, both power and data, has removed a significant uncontrolled risk from the infrastructure. Loss of either would have been catastrophic in that area due to the arrangement of the power feeder.
Bill was involved in the initial stages of that, chasing and giving contacts. So thank you, Bill.
Yeah, I know the team who moved the cables, they did have quite a lot of work to try and do them, and tracing cables couldn't sort of find things and then found things that I didn't know. So there was a lot of stuff that took a lot of time to get done.
So that was one of the biggest challenges of the job. be honest, a more mammoth task than I think we realised at the start. In fact, a lot of them are buried and then concreted and buried, and a lot of unknown cables. It took a lot to bring people together, get the right people together, and taking surveys. Collaboration is probably the big buzzword on that, but it's not only just the people you see in this room, people that are real, not in Hells, like there's a lot of work delivery, maintenance teams that don't necessarily get the recognition that they've worked on this project and we've come to the other side of it, but they've worked hard to get us there as well.
We had one of the hardest jobs we've ever done through that site because all the sleepers had shifted just with the radius of the curve. Then maybe 10 years ago they wanted it stressed. And if we decided to take the rail out, you wouldn't have got the rail back in because of the way the sleepers have changed. So I had to then square all the sleepers up. No one was comfortable with doing a sort of stick a tamper tine in and ramming the tamper forward because that's a bit frowned upon now. The only way we could do it.
I was down there doing that at one point.
You're sorry?
I was down there doing that at one point.
Right, yeah. So it was manually digging all the bays out and then putting some jacks in and pushing it forward, and that was
We did that. I remember that. I remember coming off the ship after doing that and going, they wouldn't run the office after that, to be honest. It was hard work.
it was a dreadful job, but
yeah,
it was just one of those things that you just couldn't do anything else other than. Well, I've come across a couple of alternatives of doing that now with RRVs and stuff like that, but at the time we didn't have a decent alternative, so it was a manual job and it's a lot of work to dig all those bays out because it's a lot of sleepers on both roads to try and re-stress it. Yeah.
Any more questions online?
No more on.
Try and get wrapped up.
Yeah.
We'll get kicked out. Thanks very much for that, guys. I can just ask Gary to give a vote of thanks.
Yes, thanks very much. It's good to hear the sort of final, or hopefully the final story on this big complicated job over a long period of time. And I think it's a relief to a lot of people that it's been done. So yeah, well done for doing that. Thank you.
Thanks for that,